In other words, you can print it on somewhat a curvature surface, so not really a flat sheet. So you can have a different substrate. So we have a lab at Georgia Tech, and this is the machine by Optomac, and this is really just a close-up view of this part, the print head. So you design your circuit, and you download it, and you begin to print the circuit. So let's look at some of the stuff that we can print. So you can print it on a cone, okay, with this circuit, we call it conformal antenna. Some of you might know this, some of you must be electrical engineers. So you can print antenna on this to conform to the surface of a substrate. You can print it on this material and it's flexible, okay? And you can print it on carbon fiber. Some of you are aerospace engineers, use carbon fibers. You can print it here, RFID, and another RFID, you can print it on this stretchable substrate. And the reason that is very interesting is the degree of stretch will change the resistivity on the circuits, and therefore that is the strength of the deformation, and you can use that as a strain gauge, for instance. Okay, so there are many, many applications that you can do with printed electronics and RFID. So these are just some of the possible applications with printed electronics. All right, so I just mentioned that from a defense perspective, the U.S. has the fleet of aircraft really aging, and they don't really have a good supplier base to keep up with the operations. I just mentioned that carry a bunch of parts, and very, very few are actually used. So from just-in-case inventory, carrying a lot of parts and only 5% get used to just-in-time repair. So you can print the parts, you can repair the aircraft right away. So the supply lead time will go from about as long as 28 months to about 7 weeks. Okay, so that's the ideal situation. We can really reduce the amount of time for the readiness. So some of the application, the benefits: very efficient use of resources, mass customization, rapid manufacturing, agile, fabless, on-demand production, and reverse engineering. And reverse engineering is some of the systems still in operation today do not have a supplier for some of the parts because some of the suppliers actually went out of business already. Okay, so they don't have a print, not to mention they don't have computer-aided design prints. So what we have to do is just reverse engineer, so from the remaining parts, and then we create a design for the part, and then to make the part directly. Okay? So globally, and these are the installation base. So let me just take a breath and have a drink of water. So you can see the global installation. Right now, the U.S. has about 40% of the installation, but don't expect to see something similar in 5 years. This pie chart would look very different. Yes?
Good question. So for tool or even gun, I guess no big deal. For fighter jet part, how do you compare the quality or integrity of one printed versus one manufactured in a military manufacturing?
Right. That's a very good question, and thank you for your comments. There's no big deal for evening guns. Actually, it's quite different.
Well, relatively, in terms of national security.
Right. That's a very good point. And if you wait for a few more slides, then we're going to talk about some of the challenges. Okay. So, and this is part of the good news, and then we have bad news part. Okay, actually, here it comes. So if you look at all the benefits, if you look at the possibilities with 3D printings, so can we begin to 3D print 3D printers? Okay, so that's the whole hypothesis. Can we do that right now? And actually, my honest response is not ready yet for a number of reasons. Okay, so let's look at, first of all, we have very limited set of materials we can use for 3D printing, especially for industrial use. Okay, so the second one is very small work envelope, and typically commercial machine tools can only print, well, we'll get to that, about foot by foot by foot. Okay? And third one is very low efficiency, and also the quality is very unpredictable, meaning part-to-part producibility is not there. Okay, so that is very damaging, because you want to be able to print parts in the morning, and then in the afternoon, and the following morning, and they all look the same. Okay, but right now, we are not there yet. Okay? And I'll explain why we're not there. Okay. And also a very less than optimum workflow, meaning the entire workflow is designed for machining, right? Casting, foundry, and you're machining, you're assembling. But you get rid of so many different steps. How do you redesign your workflow? How do you redesign your business? And it's a big issue, right? Because you don't want to use a new tool, but at the same time apply to an old business model. It will not bring you profit. Okay, so the workflow has to be re-examined. So let's look at it carefully now. So I talk about the different processes with laser, with E-beams, with ultrasound, and I talk about different materials, metals, plastic, titanium alloys, aluminum, steel, and we talk about, so let's look at the machine tools. So there are actually several, respectable number of machine tool vendors, primarily from Europe. Now, these vendors, none of them, and I want to say that none of them has a dominance in any of the marketplace. Okay, so all these companies are still in a startup phase, meaning they struggle and they try to achieve their own scale of economies. Very few companies, if any, has a very nice looking balance sheet. Okay, so let me put it that way. So every company is sort of in the startup mode, struggle and trying to get some of the market share. In terms of the machine tool, there are several challenges. The first one is a very limited work envelope. That's about this big. Okay, so serious commercial tool. Very poor build rate. Well, build rate is how fast you can go to build a part. Now, if let's say we can build 1 cubic inch an hour, which is about right, and for a 6 feet, 3 feet by 2 feet cubicles, it would take about 1.5 years to print it. Okay, so very, very slow. All right, of course, you would never use a 3D printer to print a solid part. Okay, so this is really a very dumb example, but I just want to bring it to the extreme so that you know it is very slow. Okay, it is a very slow process. And third one, I mentioned that it's very time-consuming to remove support material. So let me explain this. Support materials, if you print some materials, because the materials are in a not entirely solidified phase, so it is sort of metal, plastic or metal. It's beyond their melting point. Okay, so they are not very in a solid form. So the weight of the material themselves will begin to deform the whole structure. So you have to build some support as you go. So the support will have to be knocked out later on when you build a part. It's a very time-consuming to remove the support material, not to mention intelligently design the support. That's the expertise. Okay. And also part-to-part variations, and one of the audiences mentioned that the reproducibility is a big deal. Okay, it is a serious issue. So let's move on to the next one called the rapid certification. And what do I mean? Right now, almost all the aerospace parts and the defense parts are certified. Okay, so the process material are all certified. And once it's certified, you don't want to change it. Right? You don't want to change it because every time you change it, you have to go through a 15-year cycle. It's very expensive. Some of you are making composite materials. At the test coupon level, on the average, we need to make 100,000 coupons testing, 100,000 to go through. That is only the first step, coupon level. Very, very expensive. So that whole process takes 15 years. So if you can make a part from 28 months to 7 weeks, but you have to go through 15 years to certify it. So what's the point, right? So you have to have a business model to take care of that long certification process. So this requires different agencies to work together. The FAAs, if you want to do food processing, that's FDA, and many other agencies to work together in order to change how we certify parts. Okay, so I just had a slide. So this is typically how you go through the certification process at the coupon level, and then elements, and then components, and then full scale. So if you are making an aircraft, we actually have to use a full-size aircraft, 2 or 3 pieces, full size, 787 or 350, A350, to fully certify the aircraft. Okay, so the process, look at 4 years, 3 years, 3 years, 3 years, 2 years. The whole process goes to 20 years on the average, 15 to 20 years. So you don't really want to go through that process again once it's certified. So the entire additive manufacturing industry is beginning to look at here. Okay, so we need to bring in computer simulation tool, computational tools, and database, big data, and to speed up the process. So the IT, information technology, computer scientists, and different algorithms, artificial intelligence, material scientists, and all are very important in reducing the time from here to here, and reduce the number of testings we have to do, reduce the cost. Look at here, $100 to $125 million for this part alone, and to reduce the time. To compress the time, to reduce the cost. At the same time, we do not want to lose our confidence. Okay, the whole thing here is to build confidence, so that we want to buy a ticket and to sit on the airplane. Okay, so we reduce the time, effort. At the same time, we do not want to lose any confidence, if not increasing the confidence. So let's look at the next one, design for additive. Now, if you have done forging or casting, then you know this is a typical forging part, the connector, right? Now, if you want to reduce the weight, to do a little light weighting, maybe you can machine out or make a mold that you can make a few holes here to reduce the amount of materials, to reduce the weight, but not to compromise the mechanical properties, right? However, if you want to 3D print this part, you don't really want to do this, because this is still very dumb for additive. Okay, so you want to do something that, like the middle part, the meshing part. How do you machine this? You can't. But with 3D printing, it's very possible. Okay, so it's very possible. So you want to look at your part from a very different perspective. An example that I used the other day is that I used to be a very good computer programmer when I was a graduate student some years ago. Okay. And I was very good with Fortran. Some of you may not know what Fortran is. All right. And some of us know what Fortran is. And I was actually very good to program with Fortran. However, I got entirely stuck when I moved from Fortran to object-oriented programming, because the perspective is just so different, and I was not able to make the transition. So I totally gave up on programming. So I never learned how to do C++, okay, the object-oriented programming. So not to mention the modern language anymore. So this is like a Fortran, okay, and this is maybe like a Fortran 77, improved the Fortran. But this is totally different, object-oriented programming. So we need to have a very fresh perspective about how to design to take advantage of 3D printing. Okay, so that is a key. That's the key. That, I think, is where the most benefits will come from, is design for manufacturing. But very few people talk about this, and this is key. Next one is a hybrid manufacturing. And what do I mean? if you look at all the articles on 3D printing, they say, well, in 5 years, and all the machine tools will be replaced by 3D printers, right? You don't see CNC machines, you don't see anything else but 3D printers. But remember, again, some of us are a little bit more experienced. Many years ago, when robots were first introduced, and people say in 5 years, all the factories will be robots and no human beings, right? So the robots will actually get rid of the human operators, so be entirely humanless, automated factories, only robots. But look around today, we see robots, we see human operators together. It's a hybrid manufacturing systems. Again, in the foreseeable future, we see additive manufacturing, we see subtractive machining, CNC machine foundries, casting everywhere together, because every machine process has its own advantage and also limitations. So as a business owner, not technologists, but as a business owner, you really want to assemble the best tool set that you have. And additive manufacturing is a very good tool in your box, but it should not be the only tool, okay, your toolbox. So that's what I meant by hybrid manufacturing. Next one is the supply chain and logistics. Okay, so people, again, very, very rarely talk about this one. Now, if we can print our own cars in our garage, so what is to say about the car dealers? Of course, now this is a very extreme case. Okay? I don't think we'll do that. But it brings up an issue is you can make your parts very close to the point of consumption, meaning the customers, right? So you reduce a lot of inventories, work in progress. So if you can bring your production very close to your point of consumptions, using the technical jargon, it's called postponement. You postpone, you delay your production until it is absolutely necessary. For instance, if we make T-shirts for the universities, Georgia Tech is the Yellow Jacks, right? And then FSU is the Senators. So we have different. For individual sweater, no, the T-shirt shops to make this, they will not reach this scale economy. But if a company is in say St. Louis, they make a lot of white T-shirts without anything printed, and they can ship it to universities. University will put a label on it. So that is very close to the point of consumption. So Georgia Tech put Yellow Jacks, and Penn State will put their Nittany Lions and so forth. So each one will reach the point of scale economy. Everybody will benefit. So if that's the case, work in progress, finished goods in transit, in storage will reduce. That's for sure. And the stockouts and also the retired parts will, unsold parts will reduce. And feedstock transit inventory will increase, meaning you will transfer a lot of metal powders, plastics, and this raw materials, okay, in transit. The last one is the information content in transition. I don't know, so I put it just a level. Meaning, in the past, you have to track, you have to have the end-to-end visibility of all the parts, but today you don't really need it. However, you do have to have all the designs ready, okay, so that people can print your parts. Okay, so that's the information transmission. And next one is, if the merchandise are brought very close to the consumers, and the consumers will have different shopping behaviors. Right? In the past, we go to the dealers, this one, that one, will compare cars. But in the future, you only look at different designs, and then maybe you can print your car somewhere in your backyard. Okay? So the consumer behavior will change, for sure. How? I don't know. Okay, but I just don't have the wisdom to predict it. But I know they will change their shopping experience and pattern. And if that's the case, and business owners will have to look at their business models very carefully. Okay, to look at hybrid manufacturing, to look at their workflow, to look at where to use additive, where not to use additive, and how to adjust their supplier base. Next one is intellectual properties, okay, IP. Earlier this year, I went to Pittsburgh for a conference called RAPID. It's a once-a-year conference. And actually, there were several sessions within the RAPID prototyping conference that deal with IP, intellectual properties. So we had lawyers, we have this tech transfer commercialization professionals there to talk about copyright, to talk about patents. And I didn't know this until I went to the conference, is that copyright and patents are very different. Copyright is when you put words on a piece of paper which is original, creative, of your own, you already are protected under copyright. However, patents is you have to apply for and then get approved, and then you have patents. Okay, so these are very different, but both are put under the umbrella of intellectual properties. So what if I take someone's design, I print a part, and I make some changes, I reverse engineer, I create a digital design. And that design, I put it on the internet, and someone in Europe actually printed it. So who has the ownership of that part, of that design? It's very, very difficult. Okay, so think about it. This is a big issue. And at 11 o'clock is the biomedical applications. And this is, again, is we take a full advantage of the 3D printing technology. So, for starters, the biomedical applications is that you can make implants, okay, you can make prosthetics, you can make orthotics for the patients who need help. Okay, but these are just the obvious ones, very clear applications. What about this? Is that if we can print human tissues, what if we can print human tissues so that we need a liver, we print a liver, we need a kidney, we print a kidney. Okay. And I may sound, I'm joking, but this is actually not far-fetched. This is not impossible, because in the US, I'm pretty sure in other places, people begin to look at how we can print living cells, stem cells. Okay, so stem cells today are very different from stem cells 20-some years ago, okay, from 1965 or 75. The initial stem cells were embryonic stem cells, so it's a lot of religious issues. However, today's stem cells, and which is amazing, and I'm learning, is that if I need something to repair certain parts of my body, and hopefully one day we can take some cells from me, reprogram it, and then to grow it and put it on my body. What's the significance of that? Is most of the transplant is the rejection. Because of rejection of the body, right? So if we can take our own cell, reprogram it, build it, put it back in, there is no rejection. So that is really very, very beautiful. And I'm hopeful that in my life I can see this. And I think the technology is moving so fast. And this is not entirely far-fetched. But again, like every good thing, there's so many different challenges ahead of us. So let me make a comparison here so that you understand the difficulties. For every mechanical part, if you use the right material, and then you have the right dimension, you put them together, I'm pretty sure it will give you the function you want. It gives the performance you want, right?
Including no sound, probably no vibration.
Okay. Maybe I should come here. All right, so let me, can you hear me in the back? Okay. All right, yeah, we're very close to the end. So if we are making mechanical parts, so if you have the right materials, the right dimension, in the right assembly sequence, the part will give you the function that you need. However, if you want to print an organ or a tissue, it's different because the cells are living things. They grow, they proliferate, and they die. Okay, so the moment that you print a heart that looks like a heart, but in 5 days, it doesn't look as hard anymore. And most likely it will not give you a pump you need to move to circulate your blood. Okay, so for the 3D printing of living tissues, some people call it as a 4D. And the last D is the time. So when you design your heart or kidney, you need to take into account how you want the living tissue to grow, to die, to decay. Okay, so this is absolutely crucial so that it gives you the function that you need for the amount of time that it's designed for. All right? So, I mean, the people have actually begin to use stem cell to create a bladder. I mean, this has been successful. Okay, put a bladder inside the human body. So it's not entirely far-fetched. So this is no longer science fiction in my view. And I'm very hopeful, and I hope that we'll take advantage of this new technology, and if needed, hopefully we don't. Finally, the FDA approval, FAA approvals, all the policies, regulations, and IPs we really need, okay, to have a better environment so that we can actually grow this emerging technology that is going to benefit the entire human race. So what are the opportunities? Mass customization, meaning highly individualized parts, but with the efficiency and cost effectiveness of mass production. So that is called the mass customization. And also different production size, maybe a size of 1, maybe a size of 10. Okay, so not the size of 10 millions. On-demand manufacturing and expanded design space, meaning design for additive manufacturing and different supply management paradigms. So that's the end of my presentation. It's about almost an hour and a few minutes. And I didn't mention Georgia Tech Manufacturing Institute is right about 20 minutes from here. It's been around for 20-some years. Last year we changed the name. So our expanded mission is really to catalyze and accelerate innovation and the technology from the laboratories to the marketplace. So again, thank you very much for coming here on Sunday afternoon, and thank you for the invitation. I have to be back at 4. I have a meeting. That's difficult. Okay, so let me repeat the question so that people perhaps can hear in the back. So what are the practical values of, I mean, a lot of printers you can buy with a few $100s or even a few $1,000. Okay. So what are the practical values? And you can see that there's a one here, like, how much is it called? About $1,000. So Christopher is going to give you a demonstration. It's a very good question. And as an educator, the practical value to me comes from the fact that the high school students, the K-12 students can actually have very easy access to this machine so that they can actually, not just as a hobbyist, but a way to inspire, okay, their interest in science, engineering, technology, and mathematics. We call it STEM. Okay, so science, technology, engineering, and mathematics. And that is what I see as a major benefit. This is a societal change. It is, we call the makers movement. Okay, so everybody now is a manufacturer, including kindergarten students. So So it's very important, and I see really the practical value will come, will reap the benefits actually many years from now when the current high school students, junior high, middle high school students, when they move up, you'll see a substantial increase in the understanding of how things are made. And I think that is a very practical value to the society. Yes, sir.
In 3D printing, suppose I have a plastic part that requires a metal strip. How would it work? Because you cannot basically use it.
Well, it won't work today. Okay, it's it's a very difficult way. All right. The reason that I brought this part is because I have pen, and this one works best. You see, two different colors. Two different colors. Most 3D print parts is only one material, and the machine tool that we have not this one. Okay, so don't ask Christopher to print two different colors for you. This one's $500, and I print this part using a $300 printer. Expensive. It has two print heads. It can print two different materials. And the nice thing about two print heads is then you can mix the material at different ratio. Okay, so it's no longer two different distinct materials. Actually, you see the gray is a mixture of white and black. Okay, so you see gray. So you can print from very white to very black and almost a different shade of gray. Now, with plastics and metal, right now there is no machine that can do that. There is not. Okay, there is none. So right now the machines are very limited in terms of how they can make parts. So we make metal parts, we make plastic parts, and hopefully we can get the whole factory. Yes, sir.
I have a question. You said the engine permanent blade, example, and just wondering how is that the printing quality works? Is that practical? Are you going to use the blade printing and use it on the engine, or this is just still experimental?
Okay, question was the turbine blades that I showed at the video, and that's entirely experimental. Okay, it has not been qualified. Certainly, it is not certified to fly commercial or even military, and that is a pure experimental. We're not there yet. Okay, look at the materials. One simple example: metal, and then E-beam. It goes back and forth, and the estimate is each layer of material will get heat up and cool down 6 or 7 times. Because laser head goes back and forth, each one is about 100 microns. Okay, so it will go through a thermal cycle 6 or 7 times. And if you heat the metal 6, 7 times and cool it down without really good control, we really don't know the microstructural, and not to mention the integrities and properties. So we are not there yet. Okay, so we are not there. The porosity sometimes is just too high. And besides, the material we can use to make parts are very limited, only a few. And the reason is the metal suppliers like ATI or Dow, they're waiting. They are waiting on the sideline to see if they can sell the materials by truckload. But the current demand is not there. Okay, so they are not willing to jump in to really change their process. Again, all the processes are certified. They don't really want to change it. They don't want to mess with it. So this is really a very interesting situation. So coming back to a previous question is, how would this, what are the practical values? Maybe another one is you have a much larger user base. Maybe one day they will force these actors to begin to change. Maybe you take 1 or 2 more questions, and I have my business cards here. If you want to continue the dialogue, feel free to do that. Question here?
Okay, thank you. Actually, I have 2 questions. First is, you already said we have no idea about the micro picture inside the 3D printing the object. But I think also you said every layer is around the 100 micron. Whether the 100 micron is a kind of structure level or just for printing, easy printing, or the printing layer can be thicker or thinner. But
it's 100 micron is a very good thickness for every layer for consider the microstructure. Whether
Okay, so that's your first question. What's the second question?
the second question is, we all know manufacturing, industrial revolution is about energy of material. Well, when we talk about 3D, every time we say use a laser or electron beam, whether we will use actual energy just for the printing process. We don't see the energy.
Okay, all right. Two good questions. The first one is 100 microns, and who decides 100 microns? 100 micron actually is just a number that most people use, and some people use a thicker, some people use a thinner. Okay, but actually the 100 micron is about the rule of thumb that most people use. Exactly who invented it, I don't know. Okay, but most vendors actually follow that rule. The second question is whether additive manufacturing is more energy efficient or it consumes more energy. Again, we don't know. I'm sorry, we don't know. I have so many I don't knows today. But it's a good question. We are preparing a proposal to look at the life cycle energy usage. Okay, so it shows how much hypes that people have talked about, but how little people have looked at as a whole value stream. Not just a process, not just to make a few keychains. Okay, it's a whole business. The whole supply chain is nobody has looked at it very seriously. Is you reduce a lot of work in progress. You get rid of foundry, you get rid of forging, which are energy consuming. Okay, but you use laser, you use E-beam, you also use a lot of energy, but nobody actually look at it as a life cycle point of view. Okay, so that's a good question. That's a research topic, and maybe Christopher will work on it. Yes, maybe we have a question somewhere there.
Yeah, I got one more quick question.